So our third session today, we will have three speakers. Our first speaker will be Professor Hussam Mahmoud. He's a professor at Colorado State University, and he will be speaking on the resilience of healthcare systems under the compounding impact of pandemics and climate-intensified wildfires. Our second speaker will then be Professor Adam Rose, who's with the University of Southern California. He'll be speaking on what businesses can do to plan for recovery from earthquakes and climate change impacts simultaneously. And our third speaker will be Professor Negar Elhami-Khorasani, who's a professor at the University of Buffalo, who will be speaking on planning for fire following earthquakes, considering interconnected infrastructure systems. So, Professor Mahmoud, are you ready to host?
Yes. Let me share my screen. Can everybody see my screen okay?
Yes, we can.
Okay, thank you. So thanks a lot for that kind invitation to be part of this really interesting and informative workshop on resilience. My name is Hussam Mahmoud. I'm a faculty at Colorado State University, and I will be talking today about some of the work we've been doing on trying to look at compounding impact of pandemics coupled with natural disasters. I started the focus with this on wildfires, but I actually add an earthquake flavor to the discussion, since this is obviously an earthquake-related event. I will tell you I am stepping out of my comfort zone when I talk about pandemics and wildfires. I'm a structural engineer by training, and my PhD was actually on seismic behavior of steel frames. So I'm not a stranger to seismic performance of structures, but I hope that you'll find the information in this presentation useful. Before I move forward, I'd like to acknowledge my postdocs, Imad Hassan and Akshat Shuluhwat. Imad did his PhD with me on healthcare resilience, and Akshat did his PhD with me on wildfires, and they're both postdocs currently with me. So I'll start here as an outline. I'll talk about motivations, modeling the demand in general, and I'll emphasize healthcare resilience models a little bit so that you know what I mean by that. And then I will touch on the results and maybe have some concluding remarks at the end. And so the motivations are obvious, and early presentations today set the stage for why we're all gathering today to talk about this. If I kind of maybe say it in a little bit of perhaps a simple way, we have different disruptions that societies are typically face, and these could vary from infrastructural damage that would cause essentially physical disruption. You could have market collapse that would cause economic disruption. You could have uncontrolled immigration or pandemics that would ultimately impose some sort of social disruption. Well, these disasters are complex and are potentially could be single, but in many cases we've seen how we could have them occurring at the same time, actually together. We have a session on fire following earthquake, or a presentation, which is an obvious example. We had pandemics with everything you could imagine, which is another good example. Now, these hazards are characterized by high level of interaction among the different sectors. So they're not just impacting physical or social or economic, they're actually impacting all sectors together. And that interdependency is actually very complicated to model. It's not easy. And it's not easy to include in models in general. When we started to look at this, we started to look at these interdependencies in the context of compounding events. And the compounding events we were interested in was wildfires and pandemics. In fact, if you go back to early, I would say mid-2020, many articles started to surface in different news outlets talking about what are we going to do when we have natural disasters coupled with pandemics. And we were lucky enough that we started to look into this around the same time from the impact on healthcare systems. Intuitively, you would think that hospitals would be overwhelmed with patients when you have these compounded events. And the lack of medical services obviously would have a big impact on not just the people that get treated, and hopefully we manage to get them treated, but also the overall recovery. If you don't have hospitals, then you have issue with social stability for the whole community. Hospitals and schools, which both are areas we work on heavily, are considered pillars for social stability for communities. And if you look at the bottom of the screen here, this is Butte County, California, that has 4 hospitals. The one in the Northeast was called the Feather River Hospital. And that hospital was actually completely destroyed during the 2018/2019 Camp Fire in Paradise. And so what we looked actually at is when this hospital is entirely out, what happened in terms of the redistribution of patients on the remaining 3 hospitals. And now when you have a pandemic on top of the wildfires, how would that impact the different healthcare-related parameters? In this case, for example, I'm showing the percent or number of quarantine people. When the wildfire happens 50 days, 65 and 80 days after the pandemic. And you can see that depending on the relative occurrence time between the wildfire and the pandemic, you can see different variation in the number of quarantine people. And so it's a serious problem that we cannot overlook. And we've done this analysis. And then we started to ask the question, well, what's going to happen in the future when the population, when there's population growth? There's a lot of that early, Dr. Susan Carter talked about this quite a bit, actually. How would that impose additional demand on healthcare services? How would the climate change impact wildfires? Because that's also a pretty important problem that people have talked about quite a bit. There's some models out there, but we don't understand what that means in terms of damage to the built environment and what resources we might need in the future to better be prepared for future events. And so, again, we kept our analysis on Butte County, California, because it's an area where we've collected a lot of data. And of course, I'm not showing all the data because there's tremendous amount of information that would go in to present something like that. But just to give you a sense, we have the healthcare facility, we have all residential buildings in Butte County. We have physical data on transportation and utilities. We have social data related to population demographics and staff residents. You can see the red dots in the map on the right-hand side is actually showing the 4 hospitals, and the blue dots around it is where the staff that work at the hospital, where they live. And I would say, for those who are from California, I would take my hat off for how much information California shares with everybody, which makes our life very easy when it comes to modeling things. And you can see on the bottom here, we have the building, residential building, the code design. That code is relevant when it comes to earthquake, because as far as wildfire goes, when the fire touches a building, the building is gone. The size of the residential buildings would be important to determine how many people live in each one of the buildings, and that's very relevant to disease transmission modeling. And the road network is very important to understand which where the evacuation would take place and where people would ultimately live after an event. And also the population demographics is very important for disease transmission. I would point out that there's many age groups that we looked at, and you can see age group 23 is related to the age and basically the older age group. And you can see how that spikes in the year 2100. So we'll have a lot of older people, senior citizens, as time progresses. And so with a lot of information we collected, well, how do we model the demand and how do we model the healthcare resilience? And of course, that's an important question to answer. So I'll touch on some of these models. Again, there's not enough, well, there's plenty of time for the presentation, but not enough time to show everything. So I'll just give a big picture overview. So we looked first at the pandemic modeling. We developed our own disease transmission model. It's a modified EERI model that accounts for the different stages of COVID-19 transmission. And that goes from susceptible all the way to deceased cases. And all these 10 stages would be a function of time in the model. And the model considered the cases in different census tracts while capturing the interaction from individuals visiting the surrounding census tracts. And the people are visiting because when their homes are damaged, they have to evacuate and they have to go live elsewhere. And when they go live elsewhere, they start transmitting disease at other locations. And the ability to transmit or how susceptible you are is a function of the age and sex and race, so demographics becomes very relevant. We actually developed this model and assumed that people who are being evacuated are not protected, meaning they're evacuating, they're not necessarily keeping their masks on, they're not maintaining social distancing, and so on and so forth. The initial infection cases, we took that from the COVID-19 case that was reported by Butte County in 2020. Now, moving forward in the year 2100, we might get a different pandemic. We understand that, but that was not something we could predict. What would that look like in the future? And then we fed the model parameters for the recovery rates of individuals, and we used the data published by the Butte County to for active and diseased cases to estimate other model parameters. And without going deeper into the model parameters, I just want to show you the dotted lines is actual data that was reported, and the solid lines is what our model can predict, essentially being fitted to existing data, which gives us a really good fit. So in terms of looking at pandemics, disease transmission, we have a very reasonable models for these estimates. In terms of wildfire, and I know a lot of people on the call today have strong background in earthquakes. So wildfire is actually a very complicated problem for many reasons. And if you look at the wildfire propagation stages, you can actually break them down into 4 stages. You have fire ignition in the wildland, you have fire propagation in the wildland, you have ember attacks, and then you have fire propagation in the communities. And there are good predictive models out there for ignition. There is a fire ignition maps that have been developed by different entities. There is a good number of models out there for fire propagation in the wildland. There's some empirical models for ember attacks, but there's almost no models for fire propagation in communities. Some of the really good models or attempts to model fire propagation in communities have included, for example, computational fluid dynamics. But the problem is computationally, it's really expensive. So you cannot run it at a community scale. You get stuck only running analysis for 2 trees, for example, or 2 homes and a tree or something like that, which is not sufficient. And so what we did is we focused our attention on fire propagation in communities because it's also relevant to the problem we're talking about today. But it's also, as I mentioned, there was pretty much nothing out there in that area. And without digging so much deep in the model, I'll just explain kind of the features. So essentially, you have homes and vegetations that are spatially distributed in your communities. And we take these and we represent them with nodes. So we develop a graph that represents the community, vegetation, and the buildings. And then the links between the graphs, or the dotted lines between the graphs, represent the fire propagation probabilities. And these fire propagation probabilities depend on convection, radiation, and ember, which is essentially the modes of heat transfer. And essentially also, it's very important when you develop these linkage, you have to understand how these convection, radiation, and embers, how they actually change when you have structural to structural interaction versus vegetation to structural interaction. Because all of these vegetations and structures are represented by nodes. So it's really important to keep that in mind. We ultimately classify buildings as ignitable buildings and non-ignitable buildings. And then we look at the probability of ignition between 2 nodes. And we look at these probabilities, as I mentioned, which is the PTR shown in the slide as probability of ignition due to convection, radiation, and ember. Conduction, by conduction here we mean conduction within a building, even though a building also still has convection and has radiation. So we just call it conduction to be maybe perhaps a simplified way. But that's not included because we assume that once a fire reaches a building, the building is destroyed. And, we've done a few field studies that clearly showed this to be the case. So once the fire gets there, it's done. And of course, I skipped over a lot of details, but we're super excited to show that these models have produced tremendous results so far. We're super excited about this. This is actually the Marshall Fire, which happened in Boulder. And you can see the top left figure shows the map of the area impacted, and the orange nodes are basically the building nodes. And the middle picture, which says observed at the top, this is the observed damage. So the red means damaged completely or destroyed, and the blue means survived. And the predicted picture next to it is what we've predicted. And you can see that we're capturing the damage pattern really well in terms of comparison between observed and predicted damage. And yes, we're not getting perfectly one-to-one correlation. I agree with you. And actually, it would have been so strange if we had gotten one-to-one correlation. But we're getting the damage pattern very well. If you look at all the bottom pictures, these are essentially, we're zooming in on different areas to show how good the match is. And the pattern is captured pretty well. And the top right pictures here show essentially that the vulnerability value calculated by the models that we have give us obviously a very high survivability likelihood. And that corresponds really well with what happened in reality. So we calculate the survival ratio, the ratio of what survived in our model to what survived in reality. And when the model gives me a lower relative vulnerability, I get a very high survival ratio, which makes sense. And then you can see the descending, how the line is descending or the curve is going down as the vulnerability increases, which seems to be working really well. So moving forward with climate, we said, how are we going to invoke climate change? And actually, that's super difficult when it comes to wildfires. We're not done entirely doing that because there's too many aspects of it. We started with the simplest being how the wind speed moves in the future, changes in the future. There's some work out there that shows that data actually have shown decline in wind speed from the year 1970 until 2010. But following 2010, we have a linear increase. So we've used the mean wind speed for Butte County. And there was a reason why we used the mean wind speed as opposed to a maximum wind speed. And then moving forward, we kept increasing that according to this linear relationship. There was other aspect to wildfire when it comes to climate change, including drier vegetation, less moisture in vegetation. In fact, even the species, vegetation species will vary and migrate. Now that's too complicated. And there are no models out there. There's some speculations and some evidence, but there's nothing that allows us to make these changes to the vegetations. So we didn't include that. And the seismic demand is pretty straightforward. We looked at actually at the seismic history in the area. There's 76% likelihood of one or more 7+ more magnitude earthquakes striking Butte County, California in the next 30 years. The current active fault is less than 20 miles away from the borders of the county. And we collected some data on the shear wave velocity. We assumed the earthquake scenario that happened at the same fault location, which took place in 1975, was about 8 kilometers south of Orville, California. But then we actually got a magnitude 8 earthquake as opposed to the one that happened, which was not that large in 1975. And the reason why we went with 8, because the first bullet says that there's 76% likelihood of 7+ in the future. And we assumed a certain fault characteristics for the analysis. The main thing that we had to deal with is how the population grows in the future. So we estimated projection of population growth moving from the year 2040 all the way until the year 2100. And this includes 51 different demographics that vary for age, sex, and race. And the population growth is estimated as the mean of 4 different social economic pathways. And these include sustainably developed regional competitions, rising inequality, fossil fuel development. There's some work we've gotten that we took this population growth based on research that was done by someone at the University of Florida. And of course, you could use any of these population growth models. You could argue that California is very progressive in general and maybe it will remain a sustainable development moving forward. But we just, wanted to kind of maybe get an average to something to work with. And so we took the mean for all of these. Again, we're working with Butte County, California, and we looked at the county's general plan for future urbanization. We were able to get this information from online. And we calculated the number of additional buildings based on the current average of per capita per building. We kept the minimum threshold distance between the new buildings that we're adding. And of course, if you're adding both buildings in the area that are shaded here that you can see, you have to take vegetation out. And we calculated wildfire and earthquake damage based on these additional buildings moving forward. So now with the demand kind of done, how did we model healthcare resilience? So healthcare systems are very complicated. And if you look at healthcare resilience or healthcare system, it's actually characterized by the hospital itself, how it works, staff, supplies, number of capacity, or number of staff beds in your hospital. There's also the patient, the type of disease, injuries, illness, what do they have to deal with after an event? And there's also the hospital to patient connection. You need ambulances, you need perhaps volunteers to take the patients to the hospitals. What's the ambulance availability? What's the travel time, number of patients per hospital, and what's the patient waiting time? Because if the patient is going to wait for a long time, then that's really bad. And we combine sort of this waiting time idea with the staffed beds and the hospital functionality itself to compute a general functionality or general resilience term for the whole system. So if you look at the number of staffed beds, which kind of constitutes the capacity, we modeled that with a success tree that includes as a top event the percent availability of staffed beds. And it's a function of personnel availability, space, and supplies. And the space is a function of accessibility, supporting infrastructure, and working space. We need to know if nurses can go to the hospital, doctors, staff, is the transportation network functional for them to actually go to the hospital and work? Can the patients be transported to the hospitals and so on? Do we have vertical accessibility and horizontal accessibility? Do we have water, power, transportation, and so on? Do we have backup systems? So it's a really complicated analysis that requires a lot of input data. But as I mentioned in the previous slide, that's not the full story, because a big aspect of it is actually not just the quantity aspect, but also the quality. And the quality can be measured by two things: the patient accessibility and the treatment effectiveness. And the patient accessibility is a function of the travel time and the waiting time and so on. And the treatment effectiveness is a function of the minimum allowable treatment time for the patient for the specific injury that we have. So if someone needs a big surgery, we need to have enough time. We cannot just do the surgery in a few minutes and call it a day. And so you combine this quantity and quality to compute the total functionality. Now, the demand on the hospitals, of course, as I mentioned, is a function of what the patients need. And we developed this patient-driven model. In fact, in this, in one of the papers we published, we've shown that this is a well-validated model, actually, corresponds well with actual data. And so this patient-driven model is essentially allows us to compute the probability of patient I going to hospital J. And it's a function of many things, including some constraints in the future, financial, reputation, patient-hospital connection, hospital availability, and so on. But that's not the full story, because hospitals in general have agreements among them. Some do, the majority do, but some of them don't. So sometimes hospital transfer patients from one hospital to another. Remember, we have 4 hospitals in Butte County. And so what's the probability of transferring supplies, transferring patients if needed, and also transferring staff as well? And these probabilities, for example, transfer of supplies is a function of the agreement between the hospitals, the transportation system actually being functional, actually having a matching supplies that you can transfer, because if one hospital requires supplies that you don't have, then you have a problem, and so on and so forth. So now putting this whole thing together to try to kind of reflect on some of the results, I'll show you some of the results that we've obtained. So here's some of the results for population growth damage under wildfire and earthquake. So the COVID pandemic, now COVID-19, is applied for Butte County for these years, all the way up to 2100. And we calculate the total hospital inpatient overflow, untreated patients essentially. And we can see that it can increase in the future by 277% for future pandemics as a result of changing population demographics. We'll have a lot of people more than 65 years old, and they're much more susceptible to COVID. and assuming no future increase in hospital beds. In fact, there's some literature that has been showing that our hospital beds have been on the decline in the US, which is another issue to deal with to begin with. And if you look at wildfire damage, here is the vulnerability that we calculate from our model. You can see on the left and on the right-hand side what that means in terms of damage versus not damage going all the way up to year 2100. And if you reflect on this damage actually from the years of 2020 to 2100, you can see the numbers were going from 11,000 all the way to 15,000. There was a slight decline from the year 2080 to 2100 because the population demographics is actually reducing slightly. We did not remove these buildings actually from the model because we assumed that even if people might be leaving, we didn't take these buildings out. But the most important thing is that when we replace moving forward to 2100 buildings, vegetations with buildings, that actually ended up reducing the risk a little bit. From a seismic demand perspective, of course, we looked at the scenario I mentioned, and that scenario obviously is not impacted by climate change. So moving in the future, every year, that scenario stays with us. But what changes is the number of buildings moving forward in the future. So we ended up having more buildings. And this just shows some of the parameters that we were interested in: the PGA, damaged residential building in 2020, road network functionality, and casualties from the earthquake. We have 4 different severity levels. As I mentioned, moving forward, the number doesn't change a heck of a lot for 2 reasons. First, we're assuming that the buildings are increasing, of course, because the population is increasing, but buildings that are built moving forward are well designed for seismic. Sure enough, they have some damage. That's why there's slight increase according to the fragility functions that we used. But these buildings are designed well that we don't have major damage in these buildings. And so if you look at the compound disasters now, some of the results on that, you will see that we have the total hospital inpatient overflow can increase by 184% for future wildfires combined with pandemics. And you can see here the inpatient overflow versus the number of years. And you can see in the bottom figures, the 4 hospitals that we have and how the inpatient number is increasing and how that actually at the 40 days when the wildfire happens, then you start to get a jump in the inpatient numbers for your 4 different hospitals. And if you do the same thing and you look at the earthquake, you also are getting, assuming the earthquake happens 40 days after the pandemic, you're also getting big jumps when the earthquake happens 40 days after the pandemic. Large increase in the number of untreated patients, very large overflow on hospitals that we have to deal with. So, of course, the question of how do we actually deal with these increases? There's different ways you could deal with it in terms of mitigation. And before I show you kind of a couple ideas on mitigations, I wanted to show you here this interesting plot. You can see on the x-axis is the relative occurrence time between the natural disaster and the pandemic or epidemic. And on the y-axis is wildfire plus pandemic for the year 2020, all the way to 2100, and earthquake plus pandemic for 2020 to the year 2100. And we actually calculate the number of overflow of emergency cases and overflow of inpatient cases. And interestingly, you can see actually wildfire. So you can see earthquake and pandemic to be putting more demand on the system for the year 2020, 2040. And then after that, wildfire and pandemic becomes, applies more demand on the system. Also, you can see that actually, interestingly, the demand in general is the same, but it's not going to be exactly the same. It's the same in terms of number of people, but these people will have different demographics. And you can clearly see that the lighter color implies higher demand, and this higher demand is obvious when the natural disaster happens 20 to 40 days after the pandemic. We can explore different mitigation scenarios, and these mitigation scenarios we entertained reduce shelter capacity, having testing for peoples when they have to be evacuated, restrict movements within shelters, and having 6 feet social distancing in shelters. And when we kind of explored some of these mitigations, we ended up with a reduction of about 20% in the average waiting time. The reduction in staff shortage can be reduced by 20%, which is great. But the reduction in the average waiting time can also be improved by about 3%. And that's not a big improvement because hospitals are overwhelmed anyway. We can increase the hospital functionality by 50% and reduce the total number of overwhelmed hospital days by 10%. And there are many other mitigation strategies. We looked at wildfire and pandemic at year 2100 with 40 days relative intervals and the earthquake, as you can see on the bottom, and we can protect shelter residents, and you can see the enhancement ratio relative to what's existing in the year 2020. And you can see this enhancement ratio that we would have in terms of staff availability, waiting time, healthcare functionality, and overwhelmed hospital days, as I mentioned above. So you can actually end up improving your system. And there's other host of things you could play with. This is just to give you a general idea. So in closing, I would just say that providing additional staffed beds in the future will be needed based on the analysis and the scenarios we looked at. Selecting the location of future hospitals should account for the projected challenges of single and compounding disasters. And updating hospitals' emergency plan is definitely essential to be able to handle these compounded events. Protecting evacuees can help tremendously to curb the disease transmission and lower the demand on healthcare system. And of course, you have to be ready with backup system and supplies. And, in general, I would say having the availability to model things in the way we modeled it allows you to really explore different scenarios, different mitigation strategies, different alternatives, even plan for future population growth and urban planning as well. And finally, I'd like to again acknowledge my funding agencies for the work that I showed. And again, I'd like to acknowledge my two postdocs for the great work they have done so far. Thank you so much.
Thank you, Professor Mahmoud. So just want to remind everyone, if you have any questions, to put them in the Q&A box, and we will have that session at the end of our three speakers for questions. So our next speaker is Professor Adam Rose with the University of Southern California. So you can go ahead and share your screen now, Professor Rose.
Okay. Let me see which one of these. Let me see if that does it. Do I have 30 minutes? Or how long do I have?
Yep.
And thanks for being patient with me. It's been a harrowing afternoon with traffic, getting to a destination where I can set things up. But I'm very happy.
I'm glad you made it on time.
Yeah. So I'm very happy to be here today with this distinguished group. I enjoyed the speakers this morning and couldn't hear all of the next session because of some driving logistics. But the title of my talk is What Businesses Can Do to Plan for Recovery from Earthquakes and Climate Change Hazards Simultaneously. And I'm affiliated with the CREATE Center, the Center for Risk and Economic Analysis of Threats and Emergencies. I'm a senior research fellow there at Director Emeritus, and also a professor of economics and public policy in the Price School at, oh boy, that's supposed to say University of Southern California. All right. That's what happens when you do your PowerPoints late at night. So in comparing earthquakes and climate hazards, we know there are very different causes. And oh boy, hang on for a second. Mitigation then is obviously very different in preventing damages in the first place. In terms of mitigation, climate hazards, you can go all the way back to the source, and that is controlling greenhouse gases or mitigating against more severe hurricanes in terms of improving the strength of structures or moving facilities or people out of floodplains. On the other hand, recovery is very similar, because if a factory is damaged and one of its walls caves in terms of recovering from that, it doesn't matter whether that wall was caved in by an earthquake or a hurricane. You need to repair the facility damage, and you need to use remaining resources as effectively as possible. And so I'm going to proceed to define economic resilience as efficient recovery. So as far as an overview of the presentation, I'll be defining economic resilience, identifying economic resilience tactics. And I don't know if somehow this got put on a timer, but we'll do the best we can. Can then present some measures of cost effectiveness, and then illustrate effectiveness in some case studies, and introduce you to something called the Business Resilience Calculator, which is some decision support software that my colleague Noah Dormady and I have developed to help businesses cope with disasters and a whole broad range of disasters. So again, in the recovery process, you can simultaneously, with this tool, recover from climate-related hazards and earthquakes. So in terms of interpretations of disaster resilience, there are two major interpretations these days. And I guess, sorry, somehow there's a timer. I'm going to have to back up my slide each time. So one approach is to think of resilience as any action that reduces hazard losses. But there's a perfectly good word for actions taken before the event, and that's mitigation. I think the best use of the word resilience is actions taken after the disaster strikes. It's more consistent with the Latin root of the term resilience, which is resilio, which means to bounce back or rebound. Now, I've mentioned actions taken after the disaster strikes, but note you can build up resilience capacity beforehand, because resilience is really a process. You can build up your inventories, practice emergency drills, identify backup locations, but the tactics aren't really implemented until after the disaster begins. And that's what I mean by the after. Now, somebody might say, well, what can you do after the disaster strikes, after the ground shakes or the hurricane winds blow to prevent property damage? Well, you can. But property damage isn't the only indicator of costs of disasters. You can, in fact, reduce business interruption losses after the disaster strikes. And business interruption begins when it strikes and continues until you've recovered. We typically measure this in terms of lost sales revenue, GDP, and employment. And hence, resilience in another way is synonymous with business continuity. And for those of you who might be skeptical about the importance of GDP losses or employment losses, it turns out, for instance, that economic impact in terms of lost gross domestic product following 9/11 was more than 4 times the value of the World Trade Center. In Katrina, partly because it took so long to recover, GDP losses in dollar value were larger than the property damage. And I had the honor of being the lead economist on analyzing the economic impacts of the great shakeout scenario a dozen years ago. And it turns out that the business interruption losses were about 2/3 the level of the property damage there. So let me define economic resilience in 2 categories. And the first is ability of the system to maintain function when shocked. What I've done here is I've studied resilience in about 10 disciplines: economics, sociology, planning, organizational behavior, ecology, engineering. And I've found that, although there's a multitude of definitions, there are more commonalities than there are differences. And what I've presented here is a general definition, and then that is common to all of them, and then the economic counterpart. So the general definition, after Buzz Halling, is the ability of the system to maintain function when shocked. Well, the economic counterpart of that is the efficient use of remaining resources at a given point in time to produce as much as possible. So what economics introduces is the concept of efficiency. You want to minimize waste of resources. And it goes to the heart of economics. Economics is the science of scarcity. I want to give you an analogy. 40 years ago, people started talking about conservation, and they started talking about, anything you could do to use less energy, for example. And economists came on board and said, well, you can, do some drastic things, but they cost more than the benefits you receive. So they came up with the concept of energy efficiency. So this is energy savings, which pay for themselves or more than pay for themselves. They're a subset of it, but they represent that efficient core of conservation, just like the economic tactics and their application that I'm going to talk about represent that efficient core of all the recovery things that you can possibly do. So that's the static definition, a point in time. Presented these definitions many years ago. They're pretty extensive in the literature. Dynamic refers to, in terms of general definition, the ability of a system to recover and in an accelerated manner. And in economics, this is the efficient uses of resources over time for investment in repair and reconstruction, including adaptation. So in economics, we talk about dynamics relating to time. And so investment is a time-related phenomenon because you're actually foregoing some current consumption to use those funds for investment to be more productive at a later date. You're making that trade-off. The other subtle thing about this definition, I didn't say the ability of a system to recover more quickly, because it turns out, and there's a lot of engineers who've seen Chris Doble's work, and I've made the same statement in parallel, that it's not necessarily reducing the duration, because reducing the duration of recovery from the 6th year to the 5th year, there's just a little bit of savings there is kickstarting the recovery. And you need to look at the whole time path of loss reduction. And it's really accelerating recovery that is the key. So with this, in terms of the static definition, it also applies to the dynamic, but I offered this simple metric of resilience. Losses prevented by the use of a given resilience tactic as a percentage of potential losses without the implementation of that tactic. Okay, so let me give you an example. And about 12 years ago, I had the honor of coordinating 6 studies, including one of my own, to estimate the economic impacts of the World Trade Center attacks. And this was a good test run for resilience. It turns out that there are 1,100 businesses and government entities in the World Trade Center when the plane struck. 95% of them, with 97% of the employment, relocated, mainly to Midtown Manhattan and across New Jersey. Now, if all the businesses in the World Trade Center would have, gone kaput, the direct business interruption loss would have been $43 billion. On the other hand, if all the relocation were immediate, then there wouldn't have been any business interruption losses. But we surveyed firms, and we found most of the firms were able to relocate between 2 and 4 months. And so there was a business interruption loss of $12 billion. So applying the resilience metric, the avoided losses are 43 minus 12, or 31 billion, divided by that maximum potential loss, in this case, 43 billion, or 72%. So that's the metric. 72% of the potential GDP losses were prevented by the relocation as one resilience tactic. But this is only one of many resilience tactics. And essentially, I've taken what economists call a production function approach. This is how businesses transform the various inputs, capital, labor, materials, inventories, etc., their locational aspects, into the products, goods and services that they produce. And most disasters essentially cause input disruptions. So damage to the factory is loss of capital. If workers are injured or they can't get to the factory because bridges are out, that's a loss of labor. Or if they're sick because of COVID, if a warehouse or storehouse is damaged, then there are various critical inputs that are lost. And so economists in the production function are able to say, what we can do, what can we do if an input is disrupted? And here's a list of things you can do. You can conserve on that input. You can isolate your production process from it, somehow isolating yourself from the central grid, either by portable generator or solar. You can substitute another input. You can use inventory, excess capacity, relocation, can read on down. The one thing that's not an input response is production recapture, which is often overlooked. And this basically means the ability to make up lost production at a later date. And this is actually often a very inexpensive way to do this because you simply pay some overtime to your workers. But, once the electric power comes back on, if your factory is not too damaged, what prevents you from working overtime and extra shifts? So here's another example of economic resilience tactics. This is an example applied to port and transportation network disruptions, some work I've done recently with faculty at USC in engineering, Lucio Sobelman, and some faculty at UCLA in terms of looking at joint port and surface transportation network disruptions from a major earthquake hitting Los Angeles, a port of Los Angeles and Long Beach. So I've got the resilience options I just mentioned. Typically, we think of them as customer-side resilience, but this brings into focus supplier-side resilience, using excess capacity, for instance, at the port. If the port's damaged, prioritizing cargo, for instance, giving priority to perishables, ship rerouting to someplace else, export diversion, etc. Production recapture is possible here too. But another major source of supply side resilience is redundancy. And redundancy is especially expensive. And one of the points I've tried to make is that, you often build a parallel or redundant system. You never know whether the earthquake is or other hazard is going to hit. And you've got this big asset hitting there. A lot of the resilience tactics really don't need to be kicked in until the disaster is taking place, and that's a savings right there. So applying the next slide basically is some work I did with my former student, now an associate professor at Ohio State University, and we took a survey of Hurricane Harvey victims, the businesses, and we asked them which of these resilience tactics did you use? What did it cost? What were the benefits in terms of avoided lost revenues? And we came up with the cost effectiveness ratio. So if it's negative, it means they saved money by implementing conservation. And, conservation is doing more with less. So it's not surprising that's negative. Excess capacity just lays there, doesn't cost you anything. So that's a cost saving. Improving the effectiveness of management or technological change are also examples of cost saving. Import substitution, they actually make people found lower cost suppliers in the process. On the other hand, the higher negative number, the better, the higher positive number, the better. On the positive side, 14.3 for resource allocation means that the benefits in terms of revenue losses prevented were 14.3 times greater than the cost of implementing that tactic, such as purchasing or renting a portable generator in the process. I don't have time to go into that. So what we've done essentially with this is built this business resilience calculator, decision support tool. And essentially it establishes for the user a resilience index of a combination of all the resilience tactics that business uses. They may not use them all typically, and analyzes or estimates not just their effectiveness, but their cost effectiveness. And it's also able to specify the thorny issue of weights, because we're putting everything in dollar terms. And so that avoids the value judgments there. The BRC, for short, provides a checklist and scoring for resilience tactics. We can compare scores to best practice values that we have of a user of this for best practice results we've gotten from our surveys. We also have an aspect of this to update these numbers in real time as we get more and more users of this in sort of machine learning process. And then the firm also then sets some targets for resilience improvement. It's able to assess where it stands in comparison to best practice and says to itself, well, we should be able to do better. And how can we do better? What targets do we want to set? And part of the resilience calculator gives the user the possibility of accessing some information, linkages to government websites, et cetera, which will help it improve its resilience. So, and then you can use the resilience to gauge your progress. And I think I've just explained the rest of that last bullet. So this is what the resilience calculator, these are two screens from the resilience calculator. First demo version was for a pandemic, and one basically first specifies what problems did you incur during the pandemic. And so not surprisingly, employees were unable to travel to work. You had communication problems for those who couldn't. These are sort of a hypothetical example. And then you basically wind up, if you've had some experience with the pandemic, you can put in your own cost effectiveness numbers. If not, the BRC will give you these numbers in a probability distribution context, so you can gauge your basic standard, what your benefit cost ratio is as compared to the best practice case, and gives you an entire distribution for firms like yourself in a similar industry, similar size, et cetera. One of the links of all of this, the business resilience calculator, practically everything I've talked about now is at the microeconomic level of the individual business, but we want to put this in the broader context because we live in an interdependent world. Supply chain considerations are becoming extremely more important. And so we use economy-wide models to analyze all of that. And so I've got an economist definition with a lot of jargon, a layman's definition, but I can even make it simpler. Say we use a model called computable general equilibrium analysis, which essentially characterizes the economy as a set of interconnected supply chains. And we use this model. This is an example of kind of a schematic of how we apply the model. We did if you're familiar with the U.S. Geological Survey, Golden Guardian, or disaster scenarios. The second one was Arc Storm, which has gotten in the news recently. The third one was tsunami. And so this is an example for the tsunami. In the tsunami, you've got these categories of impacts in terms of closure of the entire port or long-term facility downtime or cargo damages. These feed into various micro impacts. Types of resilience tactics are given by the ovals in gray. This feeds then through the supply chain into the macro level in terms of shortages of intermediate inputs to producing sectors. In other words, businesses downstream who need the inputs. And so you've got various resilience tactics there, and all of this comes out in a bottom line number. So I can illustrate briefly how all this fits together. An example of a study we did about 10 years ago, Port Arthur, Port Beaumont in Texas, and we'll focus on the 90-day scenario. The economy, we looked at the impacts on the three-county Beaumont, Port Arthur MSA and U.S. as a whole, and we looked at the effect of 6 types of resilience. The standard estimate of what's the economic impact of a port disruption, unfortunately, is really narrow. And it basically says, well, the impact is the revenue that the port lost. Well, that's denying the entirety of the supply chain forward linkages. So once we apply a model, whether it's a more simple input-output or CGE model, we have an estimate which is 10 times that because of all the multiplier general equilibrium effects. But if we factor in resilience, we bring that down because people don't just behave passively. And so the models essentially are able to capture the effect of resilience, of short-term adaptation, to this. And you're able to reduce those losses by 2/3. And moreover, as I've given you examples before, resilience is a relatively low-cost way to reduce losses. So at that stage, we didn't factor in the cost of resilience, but that probably wouldn't have detracted that much from that number. So what resilience tactics were most important? So a lot of people talk about using the Strategic Petroleum Reserve. I passed by the one slide about Port Arthur, Port Beaumont. It's mainly a petrochemical center, petroleum refining and chemical production. So accessing the Strategic Petroleum Reserve would have only helped you about 2.4%. So it probably wasn't worth the political capital of accessing it. Using ordinary inventories of all goods, not just of oil products, but downstream, was pretty effective, as was ship rerouting, as was production reschedule. Things like conservation were pretty limited, and don't have time to get into what export diversion is, but maybe it's self-explanatory. At the macro level, we also have a decision support tool developed several years ago at CREATE when it was called the National Center for Risk and Economic Analysis of Terrorism Events. But we've always been an all-hazard center, and now we broaden the name to threats and emergencies. So this is an economic consequence analysis tool, or ECAT, and you have a user interface here, and all you have to do is press a button on which of the 9 threats, hit which level of uncertainty, hit go, and it will give you estimates. I think I failed to include a screenshot of the results here. But it'll give you a screenshot of the, if you want an interval or range, it'll give you upper and lower bound, median number, both unemployment and GDP impacts. It factors in resilience, and it factors in behavioral responses. So many disasters cause extreme behavioral responses out of fear, and it's able to factor those in to a great extent. The user has the options of specifying how much resilience, how much in terms of behavioral responses, and coming up with the estimate. This is available. My email address is adam.rose@usc.edu. And I'm happy to send you both of these tools. Just to conclude, on the recovery side, earthquakes and climate-related disasters have many similarities. Economic resilience tactics represent a very cost-effective approach to reducing disaster losses. And it's important to consider both, though, individual businesses and economy-wide or supply chain consequences when you make decisions on disaster risk reduction. And there's a need to balance pre-event mitigation and post-event resilience. So, I'm not an engineer, I'm an economist, so maybe I have my bias, but I think there's a lot of emphasis on mitigation, all these low-cost ways you can reduce losses, business interruption losses through resilience are often ignored or not fully appreciated. And I think if they're brought in, one can strike a better balance than we have now. So thank you very much for being a good audience and being patient with me for being a bit late to the show today, and also whatever gremlin snuck into my PowerPoint. Thank you very much.
Thank you, Adam. This is Alvaro Celestino, and thanks, Jana Ponfiglio, for taking care of the moderating for the first 2 speakers. For some reason, I cannot show my screen. Now I can show it.
So I need to stop my sharing first.
Yeah.
That's probably what you got.
Okay. Our next speaker is Professor Negar Elhami-Khorasani with the University at Buffalo. And the name of the presentation is Planning for Fire Following Earthquakes, Considering Interconnected Infrastructure Systems. Thank you, Professor Negar.
Thank you, Alvaro. Let me share my screen. How about now? It's all good? Yes.
Yeah.
Perfect. Thank you. Thank you. It's a great pleasure for me to participate in this panel with Professor Rose and Professor Mahmoud. And it's been great to see all those presentations throughout the day. So I'll be talking about fire following earthquake. We've heard from the previous presenters on the importance of cascading and compounding events, as well as the interdependencies between infrastructure systems. And those are going to be a focus of this presentation as well. So the theme of this event overall is the impact of climate change on communities. Now, as part of my other research, I study the impact of wildfires on communities. The number and frequency of these destructive wildfires have been increasing. And there are some differences between wildfires and fire following earthquake. However, some of the fundamentals of fire spread are the same. So there are things we can learn. And after the 2017 Tubbs fire in California that affected Santa Rosa, several discussions came up about what if we experience fires following earthquake, which is possible, and we've seen them before. So this presentation, I am going to focus on basically what's a decision-making framework for resource planning and response guidance to address the cascading effects of post-earthquake fires. Now, we've observed several earthquakes followed by fire events where the fire causes significant damage. For example, the Northridge earthquake in 1994, there were about 110 structurally significant fires after the earthquake. This is the same image, I believe, that Professor Mahmoud had in his presentations, the 2011 Great East Japan earthquake, where the fires consumed blocks of the community. So how can we model and capture the relevant processes that to predict basically the impact of fire following earthquake? Now I'm going to start at the building level, which is shown in blue in this figure. Fire may ignite within the building due to ruptured gas lines, electric arcing, toppled furniture, and so on. And at normal conditions, we have sprinkler systems and fire compartments within buildings to contain the fire spread. But depending on the building response during earthquake and the level of damage that the building experiences, we may end up with damaged passive and active fire safety measures that are no longer effective. So the next line of basically defense is the firefighters basically showing up at the site to suppress the fire once the fires are ignited. Now here we're dealing with layers of infrastructure networks that have to be functional, that are shown again in green in the figure. Now these firefighters need water to fight the fire, but damage to the water network or dependency of the pumps in the water network on power could be an issue after an earthquake. And again, this was something that was observed after the 1994 Northridge earthquake. Roadway accessibility is another issue after an earthquake because of damage to bridges and debris on the roadways. And the key here in this framework, what we're looking for is to find the weak links or the vulnerabilities. And this, I would say, system of systems approach to improve the performance, basically, of the system. Now, it's a complex problem, has several layers of networks and infrastructure, but given advances in computational power, we can now approach and model these complex systems. Okay, concerning the time constraint, here half an hour, I'll provide a brief sort of big picture overview of these different models, layers of information, and then apply that integrated framework to a case study. So briefly, in terms of first layer, ignition model, As I mentioned, for damage to utilities such as gas and power lines, as well as structural and non-structural components of a building, are pretty much primary sources of post-earthquake ignitions. So what we've done, we've developed an ignition model that is data-driven. And this data comes from 7 historical earthquakes, all of which happened in California, and they occurred between 1983 and 2014. Now, the model uses this logistic fit to the data to relate probability of ignition to peak ground acceleration, type of building material, also main features of the environment where the buildings are located, including square footage here and population density. And this proposed ignition model can be used to estimate the expected number of post-earthquake ignitions in a region. You can see how by increasing the population density, we have higher probability of ignition. Increasing square footage, we get higher probability of ignition, and obviously larger earthquake intensities cause more number of ignitions, or greater likelihood of ignition increases. Okay, so moving on to the next layer, transportation network. And here the objective is to evaluate the travel time of the fire engines from the location of ignition to, from the fire department to the location of ignition, considering damage to critical bridges in the region and the debris accumulation on the roadway. So let's talk about bridges first. We put together a comprehensive database of bridge fragility functions in order to be able to estimate damage. And this detailed bridge taxonomy, we proposed this to consider substructure, superstructure characteristics, as well as parameters that would influence the demand. I want to point out one thing. Yes, this is detailed, so knowing the type of the bridge, we can come here and pick the relevant fragility functions. But I want to point out here at the bottom, the deterioration, environmental deterioration and aging during service life has also, so the impact of those on bridge damage after an earthquake has also been studied by a few researchers. And that's something that we should account for as we move forward, especially again, considering that here the theme is impacts of climate change. So we created a user interface. We put together everything, all the fragilities. We have 88 sets of steel and 127 sets of concrete bridges. And it gives us, it basically helps us compare different fragility functions for different bridge classifications. And we can narrow down the category of these relevant fragility functions based on the taxonomy. It's possible to harmonize those functions that have common characteristics. We can also basically export this, what we obtain from the user interface to a text file or as an input to our model. And for the purpose of fire trucks crossing a bridge, functionality is defined as either complete in case of slight or moderate damage, and they basically functionality goes down to 0. They cannot cross a bridge if there's an extensive or potential for collapse. Next is the debris model, and whether roads are covered with debris from buildings or not. Why do we care about that? Well, in a densely populated area with a number of tall buildings, I'm talking about downtown areas in the West Coast, glass debris, for example, from building envelopes could cover parts of the roadway. So what we've done is we've calculated roadway accessibility as a function of generated building debris from an earthquake, which is described probabilistically in terms of building volume. So we actually had data. So there's existing data on debris mass fraction. So what would be the mass of the debris from structural and non-structural building components? And they're available in HAZUS. So we're using what's available in HAZUS, and then we're converting those mass fractions into volume fractions. And this debris, both from structural and non-structural components, depend on the damage state of the structure, which is given as a probability. So it's going to have a very extreme damage, or it can survive the earthquake, multiplied by that debris fraction that comes from HAZUS. Now, accessibility. So we get these volume fractions, and then we combine them with potential schemes for how they could actually end up on the roadway. And that way we define the accessibility. So we look at, okay, what's the debris width? Is it going to be less than the curb distance? Then the roadway is pretty open for the fire engines to go through. And then it goes all the way to 0% accessibility if the debris width covers much of the roadway to the point that a truck cannot pass through. Here's a quick example. This is not the case study. This is just a simplified or streamlined example to show how this applies. This is a virtual community. This is a centerable community that was also mentioned earlier in the morning session. This was designed as part of the NIST, Community of Resilience Center of Excellence, and each node here is a neighborhood with specified building inventory. And there are 2 fire stations. So fire station, there's node number 2, there's a fire station, and node number 3, there's another fire station. And then there's a hospital here with the green dot. And primary roadways are shown in, with lines, and anything that's dashed, it's basically there's a bridge there for connection. Now we established a service area for each fire station and then studied the increase in response time. So how much that response time changes after the earthquake. Now these nodes 9, 10, 17, 24, and they're also shown here in blue, green, yellow, and red as a function of PGA. They experienced increased response time at higher PGAs, either because of damaged bridges with no access due to lack of redundancy in the roadway. So if you look here, these 4 nodes we have, and then we have bridges all around. So there's a potential for creating an island with those nodes if all those bridges, in the case of an extreme earthquake, they get damaged and go down. And it's also interesting to note that nodes 6 and 8, they have the highest population in this virtual community. Therefore, they are more prone to post-earthquake ignitions. But given how fire departments 2 and 3, they're located near those neighborhoods, it actually brings the vulnerability down. Okay, very quick about the water network. So at the time of extinguishing the fire, firefighters basically rely on the availability of water flow and pressure to suppress the fire, which could be degraded as a result of earthquake damage. So we need to take that into account. So we start looking at damage at different components of the water network. These are water reservoirs, pumps, and so on. And we use a capacity index to aggregate and map the information from probabilities of having different damage states to the level of functionality. So given an earthquake intensity, we have different likelihood of damage states. If something is not damaged, then it has full functionality. If something's completely damaged, it has 0 functionality. And then in between, we have a function, percentage of functionality. And that way, we basically get the functionality of a component. And with that, then we can conduct network analysis to obtain water pressure and flow. So we are using existing approaches in the literature. So the water pressure and flow in the network are evaluated using well-established gradient method in conjunction with pressure-deficient network algorithm. And here's a comparison, what I want to show in this figure. This is, again, another streamlined example. I get to the more complicated case study later. But here's the water pressure in the network after the earthquake as a function of time, as a function of as well on the earthquake intensity. So as we go up, PGA of 0.5, we see the drop. So this is before, or PGA of 0.1, higher intensity, PGA of 0.5, we see a drop in pressure. And this red line indicates a threshold where if we go below that, the fire department, it's harder for the fire department to draw water from the network. And this limiting pressure is typically 20 PSI, it's defined as 20 PSI. Okay, let's talk about fire spread. Now here I'm going to go a little bit more into detail. We start with the plan layout of the buildings that can be extracted from high resolution municipal data sets. The generated raster matrix should provide, should provide a realistic and detailed building layout with no loss of information at the building level. And why is that? Because we need to know all the buildings and the separation between them, because we're going to capture fire spread between the buildings. So that distance is important. Then we compartment the buildings into 10 by 10 by 3 meter cube resolution to track the fire spread within the structure. And then we also introduced this ray casting algorithm to detect buildings that are exposed to a fire source. So if there's a structure on fire, then we want to know what other structures could be exposed to that energy or heat from that source. And obviously, again, it's a function of distance. I'll get to it. But that ray casting basically algorithm tells us what could be exposed. Now, we have to consider fire spread within buildings and between buildings. Here, I'm talking about what's happening inside a building. In terms of evolution of fire inside a compartment, the time temperature evolution you see here at the bottom, the top is just the energy. It depends on the amount of fuel and ventilation condition. And ventilation condition, basically, it's about supply of oxygen to have that fire going. We've generated 625 probable cases considering variation or uncertainties in fuel and ventilation. And then we can randomly assign these scenarios when running thousands of simulations across a community. In terms of fire spread rate, again, across one floor in a building that goes horizontally, and then it could go vertically between floors. We are relying on observations from past fire events. I will note that damage to non-structural components within the structure could accelerate fire spread within the building. Now let's look at fire spread between buildings. Professor Mahmoud also mentioned these as part of his presentation, so I'll try to be brief here and quick. First is the thermal radiation. That's one of the short-range mechanisms of fire spread, and it's basically the amount of heat flux that's received from thermal radiation at a surface, and that can be calculated just using the physics of the problem. Another mode of heat transfer is turbulent fire plumes. So there's a fire, then there's a plume, and that is a convective source of heat flow. It contributes again to a short-range fire spread, and it depends on the wind speed and strength, and it can increase as basically the plume can increase temperature in the downwind direction. Okay, then we have the direct flame contact. That's basically when we have flame moving and touching the structure. We have considered the contribution of direct flame contact only for timber structures. And finally, we have fire spotting, which is a primary driver of spread in wildfires. And we are using actually our models for the fire research and applying it here. Basically, you've got these embers that are generated. So there's a generation, then they're transported, and finally they land and cause ignition. And for this case, we are just using data-driven models for all three mechanisms within fire spotting. Okay, then we're almost done with the methodology. Here's the suppression. So the model, once you've got a fire, then fire department shows up and starts to suppress the fire. This is again based on the physics of the problem. We look at conservation of energy, momentum, and mass in a control volume. Our control volume is basically the compartment that's on fire. And what's happening is that we have energy of the fire, the rate of energy that is consumed by water, and we do have some exchange of energy with outside. So we put all of that together, and what we solve for the time that it takes for the fire department to extinguish that fire. So we want to put everything together that I've talked so far and presented so far. It's this decision-making algorithm. The fire department needs to decide how many engines should be assigned to different locations of fire. And possibly there will not be enough engines to report to all those fires. So what we're going to do is that decide or assign fire engines from wherever they are to the location of ignition. And then once they're at the location, they also need to decide at what compartment they're going to start fighting the fire when several compartments within the building are being consumed. So we guide this assignment by maximizing the coverage cost and basically minimizing the travel time. Parameter C here is a normalized cost value of the buildings with respect to all the total cost values of all buildings on fire. So we're going to pick structures that have larger appraised value. T, parameter T is the normalized response time. We want to make sure that we assign fire department or fire engines to locations where they can reach that location. And finally, parameter W relates to availability of water. We want to assign them to locations where the water is available. So this put together everything that I've presented so far. Now let's apply the framework to the case study. Now here's a realistic case study. It includes 600 buildings or a few blocks of a downtown city on the West Coast. It's an urban area with most of the buildings being non-combustible. Here's a closer look at the building inventory. There are 6 census tracts within the neighborhood we're studying. They're color-coded here. And we have a distribution of low, mid, and high-rise with a good portion of high-rise. We can see the color here. Our structures, we do have majority of them post-1970s. Again, that's gray and white-ish color. And finally, most of our structures are steel, concrete, and masonry, meaning non-combustible. We do have some wood that's shown in black, but majority are actually non-combustible structures. Okay, here's, one more slide here. We have the inputs. This is the building layout. This is the transportation network. We have introduced 2 fire departments within the region, one here at the top, here at the bottom. And here's the water network. And what you see here is basically the recreation of those buildings. And you see we have many high rises within the area. Here's one sample running one case. So I'm going to show the results for many, many cases in terms of the probabilistic attempt. But it's just to show how it works, the simulation works. Now it's running. So what we have is that we have the model generates number of ignitions, and then the fire engines are basically deciding to go to those locations of ignitions. And in this case, you're going to see that the rate of fire spread is actually faster than what the resources can handle. Their simulation will continue for 8 hours without any successful suppression. So from the fire department, these are the paths that the engines traveled. Anything that's red, it's still fire spreading. Anything that's blue, these are successfully suppressed fires. And you can also see on the 3D view that there are some red parts going on. Those are the fire spread. And this is the just not from the earthquake. This is just direct losses from the fire events that are happening. And this is increasing, and it's going to go on until up to 8 hours where we stop running the simulation because at this point we know that we don't have enough resources and the fires are just going to continue spreading. We'll let it run for a little bit more. We're at a time 6 hours. I have about 5 minutes, so I'll be on time finishing. Okay. So let me go on. Now, what I want to show is that, on the next slide, there's some set conditions for this one simulation, right? But still, everything in the background in terms of fire spotting or in terms of number of parameters, if the damage to the buildings, damage to bridges, debris, all of those are probabilistic. So given the same input, we could still come up with successful or unsuccessful suppression. Just because of randomness in all the parameters that go into the model. And that's why we would need to run many simulations in the order of thousands of simulations in order to get an idea of what would be the probability of success or not. So the performance of the fire department is characterized in the form of these fragility functions. And our performance metric is the probability of unsuccessful suppression. We want to know what's the likelihood of unsuccessful suppression. And then we change some did a parametric study. So if we have limited resources, if we have higher utilization time, which means that the fire department doesn't get to site, and it takes longer for the fire department to get notice that, oh, there's a fire, and then by the time they get to the location, start fighting the fire. if that's longer. And then if there's a faster rate of fire spread inside buildings, it definitely causes more damage. You have a higher probability of unsuccessful suppression, which gives us an idea of that. If you let the fire spread at the beginning, right after the earthquake, then it becomes out of hand and it's harder to suppress it. This is also reporting losses. Again, just based on fire, we're not adding the earthquake part here. Number of affected buildings and the cost of those buildings associated with appraised values as a function of PGA and as a function of time after the earthquake in terms of how much, if we can suppress the fire. And again, this faster rate of fire spread inside buildings. So if we have damaged non-structural components within our walls, our ceilings, they get damaged and you're going to get faster fire spread. And again, the fires are going to go out of hand with a higher probability of unsuccessful suppression. So with that, in terms of summary and conclusions, talked about basically capturing an explicit interaction of spread and after an earthquake and the emergency response. And one clear, basically what comes out of the results is that fire should be controlled at early stages for successful suppression. And for sort of planning and mitigation upfront as well as the response. So something like this is also we can plan if it happens, how to assign fire engines to minimize our losses. This kind of framework can be used. This is a dynamic, basically, decision-making algorithm. And redundancy in our infrastructure systems, such as transportation and water network, would be helpful for the fire departments to be able to get to those locations where the ignitions are occurring and suppress the fire. Now, obviously, this research would have not been completed without my students as well as collaborators. This was a collaboration with Professor Maria Garlock at Princeton and also the data from number of institutions in the city of Seattle. We appreciate that, and also USGS, the funding agency for this research. So thank you. And one last note is that a lot of basically this presentation evolved around networks and community, but inside one building, if you have in our audience structural engineers who are interested in fire following earthquake within a structure, AAC, SEI, Fire Protection Committee recently, we put together post-earthquake fire assessments of buildings, sort of a framework, and now that's published and out there for the audience. So with that, again, thank you, and happy to have answer questions and discuss with our panelists.
Thank you, Professor Negar. Let's start then the session, the question part of the session. The first question is the business resilience calculator available to the public, or at least to us? I guess they mean the audience.
It is, and I had a link to it at the end of my slide, so let me bring my slide up just so I can look at it again. Are you going to post the slides, organizers? Are you going to post the slides?
I think we will post the slides, yes.
Okay. So I need, first of all, just use some revised slides. But the other thing is at the next to last slide, there's some references to the work. And so the resilience calculator is just resiliencecalculator.com, all lowercase. Punch that into your search engine and you'll get a copy of the calculator. You have to sign up for it, but no cost. Again, resilience calculator all together, no space.com.
Okay, I sent it. Then the next question is, let me just put this back in. But if any of you want to share your desktop while answering, that's okay too. I'll put it here. To Professor Rose, again, can CGE model and other tools you presented be used to predict how to best allocate disaster relief funds for businesses that lead to the fastest recovery of the community as a whole?
Potentially, yes, but that is a very heavy lift. One of the things a CG model can do that's useful is because it characterizes the economy as a set of interconnected supply chains, it can show you kind of the total implications of your decisions. So you might have two factories side by side, and one of them producing two different products, and one of them would cost 10% more to recover. And you might say, well, let's pick the one that's least costly to recover. But that business may have very little connection with the rest of the local economy. It may primarily be exporting its product. So if you want to get the economy back on its feet, you need to identify the business that contributes most to the local economy, regional economy, and favor that one. And the model is able to tell you things like that on a sectoral basis.
Thank you. This one is for Professor Negar. What can building code do to slow down the fire spread after earthquake within the building?
Thank you. So I'll start. I'll get to building codes, but basically for fire following earthquake, number one is you want to prevent the ignition, and with that, we already have, for example, automatic gas shut-off systems and things like that. And then within the structure, you can have introduce bracings to appliances and so on to prevent the ignition. But we cannot have, we cannot assume that, okay, there won't be any fires ever. Most of the time something goes wrong. So then we have the building last sort of a resort that we fight that fire. The key is to stop the fire spread. And for that to happen, we need, again, our non-structural components to function properly, such as, again, walls and ceilings, and even our passive fire protection. Let's say you've got a steel structure where you have these passive fire protection systems, that you've got sort of an insulation on the steel that could come off during an earthquake. So right now, the code is primarily the way that it's been, it prescribes the guidelines. It's for collapse prevention, on life safety. But there are a lot of discussions on functionality and continuing functionality and recovery and so on. And therefore, we are moving towards that direction. And all of that would help with something like fire following earthquake, because then you have your non-structural components that have less damage, and thus would help with this compartmentation within the structure that prevents fire from spreading. Alvaro, there's also a question I see on there.
Yes.
It's on the other chat, right? No, there's one in the chat.
Oh, I'm sorry. Can we maybe go with my question that is kind of related to what you just said?
Definitely. You're the moderator. You're the boss.
Well, it's related to that. It's basically, I understand everything you said is right. We seem to have built the codes from experience, but we never had the 50-year lens to see what was going to happen in the future when we created those codes. So there's all the codes have their plus or minuses, let's say. So in the case of non-structural that you mentioned, have you guys run any models, assuming, for example, that the code is a little more stringent? And if it were more stringent, you can observe that it's definitely less spread.
We run a model. I can, if you want, quickly share my screen. This is answering your question, but it doesn't actually have So what you see here is the structure, and then just one building now, a multi-story steel moment-resisting frame from the structural point of view. And then we have these walls, so the blue, and then the doors. And then what's happening is that if you lose a wall, not completely, but it's damaged enough for the fire to spread, then it's going to cause fire spread within that horizontal within the floor. And that is a function of, again, interstory drift as well as the peak floor acceleration, right? So what we have run so far, it's based on the current available, like what's status quo, what we have, rather than what, if we improve them, what we would see. And at least just keep it short, overview, this fire spread within the structure and the damage to non-structural components, they do make a difference. We do have different, like, let's say the fragility of our windows. If we change the windows typically eventually breaks down once the fire starts because of pressure differentiation and so on. But if we even delay that with a better type of window, then that could still have some impact in terms of delaying the fire spread and being able to control it at early stages. So hopefully that answers your question.
Yes, it does. It seems that reducing drifts, it's good for everything, or many things. So if we jump to then this, we have a question here that asks, firefighters do more than just fight fires and may be allocated to evacuation. Is this aspect considered in this model?
Not explicitly, but indirectly, yes. And that was the utilization time in terms of how long it's going to take them. So the utilization time takes into account the time that they know that there's a fire and they get the crew ready and the crew starts to, get ready to go to the location. That's separate from the travel time. But, and then as well as the number of resources. So again, indirectly, it does take that into account. If you reduce the number of available resources that would just specifically go fight the fires, then things blow up in terms of fire spread, goes crazy. So yes, but based on conversations with actual, firefighters on the West Coast, if they know that so evacuation is really important. That's very true. But if they know that their fires would potentially spread going out of hand, they would, the emergency basically response office or their control office making decisions, based on their evaluation, they might prioritize that fire spread in order to confine the fire. Depending, again, they have to make a decision, I guess. And that's why we came up with this framework, because right now it's a little bit more based on experience of, okay, where are we going to go? Whereas it would help them to have more systematic, quantified approach.
Alvaro, there was a question that was in the chat. It's what is the source of your building inventory data? That was for Professor Negar.
Thank you. So the source of some of the information, such as location, longitude, latitude, and construction type, construction year, they come up from open, available municipality websites. In this case, it was Kings County, so they're available. The key information that sometimes, depending on the location of doing the study, so if we move out of Washington to in California, depending on the city, is the structural system. That typically, it's not available on open sources, so we have to start having conversation with the city. And then it would be really helpful if the city already has that kind of data digitized. If not, then you kind of have to go through their archives structure by structure, trying to figure out, okay, is this still moment resisting frame or brace frame? Because that impacts the earthquake response, which impacts the cascading event, which is the fire, and how that's going to spread.
Yes, and I may add, you know probably that in several cities in California, there's also already some inventories done by the city with different private contractors, like in Southern California or Northern California. And I'm not sure if that information is available, but it exists. Any other questions? Okay, we then will finish the session. Thanks, Professors Hussam, Adam, and Negar for your participation. And we are gonna resume the presentations at 3:30, I believe.